This is the source of the nuclear leak at the nuclear power plant in Japan. Replacing nuclear fuel, inside it contains uranium-235. Don't underestimate it just because it's a small bundle. The amount of heat released is equivalent to over 200,000 liters of oil. The electricity generated by it is enough for an average family to use for 100 years. So how does it generate electricity? Why can workers handle it without any issues? And what is the issue with nuclear wastewater in Fukushima, Japan? After watching this video, you will understand completely. These black powders are extracted uranium-235. Then, using tools with several tons of pressure, it is compressed into a solid rod shape. Then, it is sent into a kiln by a conveyor belt for sintering. This process is called sintering. After sintering, the solid will harden and form a block. It will shrink and increase in density. After that, the casing will be coated with a layer of ceramic material to provide physical protection and enhance radiation shielding. The sintered rods will be placed on a tray by a mechanical arm and neatly arranged into sequences, easily poured into these fuel tubes. These nuclear fuel containment tubes are made of zirconium metal. Zirconium has a high melting point, is corrosion resistant, and has good thermal conductivity. Therefore, in nuclear power plants, it is widely manufactured into tubes used to contain nuclear fuel. The process of packing nuclear fuel into metal tubes is completely automated. Incidentally, nuclear fuel consists of uranium-235 or 238 and plutonium-239, etc. However, for economic reasons, most nuclear power plants use uranium-235. The nuclear fuel containment tubes will be transported to an automatic welding machine here. Each fuel rod will be sealed by welding. After that, it will be transferred to a fixing device. A fuel rod bundle has a total of 37 rods stacked vertically. Finally, during the process, ensuring each bundle of uranium has the correct content. Why do workers dare to handle it like that? Because these nuclear fuel rods, before being put into the fission reaction, have very low radioactivity, coupled with being encased in metal or ceramic, they also have a certain level of shielding. Workers also adhere to safety procedures, so there are no major issues. After being properly packaged and processed, the next step is to be transported directly to the nuclear power plant for power generation. How does that nuclear power plant use these fuel rods to generate electricity? These are the nuclear reactions you often hear about. Each cylindrical tube like this is a nuclear fuel rod that has just been sent. It will undergo nuclear fission here to generate electricity. Why is it not like an atomic bomb? Why is there no nuclear explosion? The nuclear fuel in an atomic bomb is concentrated in a supercritical mass. High-density nuclear fuel allows for an extremely rapid, uncontrolled chain fission reaction. Meanwhile, nuclear fuel rods in nuclear power plants are designed to be long and slender to have enough space between them to separate the decay of neutrons among the nuclear materials to slow down the fission rate. Of course, the biggest reason is that in addition to the nuclear fuel rods in the reactor vessel, there are also control rods inserted. They are made of materials such as boron, chromium, or thorium. Their main feature is high efficiency by adjusting the depth of the control rods when inserted into the reactor vessel to absorb the control neutrons, achieving regulation and chain reaction control. The principle of nuclear fission has been explained in previous atomic bomb videos. It has been explained, so it doesn't need to be repeated here in detail. In simple terms, nuclear fuel fission can generate a large amount of heat. Then by pouring water into the vessel to soak the nuclear fuel rods, preventing them from exploding at high temperatures. Then increase the pressure with these two red pressurizers, raising the boiling point of the water to over 300 degrees to prevent boiling inside the vessel. The hot water inside the vessel is then pumped through pipes to circulate in the evaporator section, returning here to the evaporator section. It is cooled by a closed heat exchange pipe, not directly contacting the water inside the evaporator section, because the evaporator section has standard atmospheric pressure, so the water easily boils, creating high-pressure steam, which is then sent through pipes to the steam turbine generator. You should understand this principle, similar to the pressure cooker we usually cook with. When the water boils, it creates high-pressure steam, using the power of high-pressure steam to push the generator to rotate. The generator is then driven by the steam turbine to generate electricity, which is transmitted through the transformer station and transmission lines, then returning to the steam turbine generator. Through the lower pipes, the steam that has released its energy flows into the cooling section. High-temperature steam meets the cooling pipes of the cooling section. The steam condenses back into water, which is then pumped through the lower pipes to circulate back to the evaporator section. The water in the cooling pipes will be transferred to the cooling tower for cooling. Now you should know what nuclear contaminated water that Japan discharges is, right?